1995 Acura Integra. I want to walk you guys through an ABS issue that we did previously. I really wish I would have filmed this from the get-go because it was really cool what we found. So I'm going to try to duplicate the symptom and walk you through what we did. And the first thing is going to be getting trouble codes out of it. Don't jump that just yet. First thing is going to be getting trouble codes. And the way we do it is we look at the ABS light on the dash. So I think the first thing would be make sure that the light lights, be key off, turn your key on, make sure your ABS light is lighting. And the next thing would be the same 2-pin connector. Let me get you a shot. The same 2-pin connector that is under the dash that's used for the check engine light flash codes is the same one that we jumped for the ABS system. And we're just using a paper clip. And so we're going to jump those 2 pins together. And what we should see is our trouble code on the dash. Now with no codes in memory, you can see that that light actually went out and is not flashing. So that would be what no codes look like. Go ahead, take the paper clip back out. Okay, good, put it back in one more time. So I think that's important to know is what no codes looks like on your ABS system. The ABS light goes out, does not flash a code. So now at this point what I need to do is I need to reset the code that was in here and show you what that one looks like. Alright, I've reset the trouble code that this car had. Again, I wish I would have filmed this from the get-go, but we're recreating the fault that we had. So there's a code in memory. We're going to jump it right now with the paper clip. You got to watch closely. There's 1 flash, a pause, and then 2 flashes. So on a typical system, that'd be a code 12. This one's a little bit different. I'll take you to the trouble code sheet here in a second and show you how Honda lays these out. And you see it's not flashing anymore. So if you miscalculate that, just take the paper clip back out. Go ahead and do that. You see the ABS light come back on, and go ahead and put the paper clip back in and watch your sequence. There's 1, 1, 2. So you saw the short pause between the single flash and double flash, and so that's either going to be a code 12 or in this case it's a 1-2 code. I'm going to take you to the list now. Something I failed to mention to you guys before I grab this flowchart or code description list. When we started with this ABS light would not flash when we connected our jumper wire. And so the direction that we chose, because it wouldn't do anything or wouldn't react, is we wanted to go to the ABS computer and verify powers and grounds, and we were missing a main power feed to our ABS control unit from a cable under the hood. Let me get you a shot of which one. And it was this cable right here that goes to this junction box. This cable was actually disconnected, was never connected to the terminal. We did not realize that when we went into this. So the hard part about shooting this after the fact is which direction we picked and why we picked it. So I want you guys to be clear that the reason we went to the computer and didn't check anything under here was to just pretty much kill 2 birds with 1 stone. Is let's check our powers and grounds at the computer itself. And you know, you wouldn't have been wrong checking them up here. There's your main feeds are up here, the relays up here. But in the case of checking powers up here, most commonly everything would be good up here. And so you'd have to go to the computer anyway. And that's what I meant by killing 2 birds with 1 stone. We went to the computer next, and I want to be clear on that direction and where we went from there. So for this video, I'm going to exclude the power and ground tests that we've done on this unit. I'll get you a shot on the diagram and show you where they are. I'm not going to walk you through that part. What I want to walk you through is this 1-2 fault with this ABS pump. Alright, just like any other computer system diagram, checking powers and grounds is very similar. I have the grounds marked up here in green, and my power feed I have in pink. So we have 2 main power feeds coming in. This one's battery, this one's ignition. And that's what we went through, and what we found was our battery feed here was missing, and that took us back to this fuse box, which I just showed you under the hood. and what we found is the main wire was not connected, so this whole box was dead. There was no power on this hot all the time circuit that's showing hot all the time that comes right from the battery. Once we fixed that, then we were able to do our paperclip, we were able to jump the lead, and our light flashed at us, and we got our 1-2 fault code. And what I said in the last segment or two was that some of these systems, when you see a single flash and then a double flash, that it is a code 12, but in this case it's not a code 12, it'd be a 1-2. You got a single flash and then a short pause and then a double flash. So 1-2, and the definition of that code is a pump motor circuit fault. So the next thing at this point for this trouble code is to pull a flow chart, and I've done that. And of course, like other flow charts that we love, it is pretty elaborate. It's 15 steps. Not too bad. This one's only 2 pages. It's not 30 pages like some of the other ones. And just going to walk you through this first step and show you how we checked it. Actually, I think we looked at the diagram first, but I'll walk you through the flow chart. We'll go back to the diagram, see how this motor's controlled. I generally don't jump at the flow chart right away. I'll look at a wiring diagram first, but all right, so step 1 on this diagram says check ABS fuses, replace as necessary, remove pump motor relay, test the relay, replace if necessary. So right away we're doing a relay test. And what they have us doing for the relay is basically jumping it, bypassing it. I printed that. You see this is kind of a different color here. This relay test is basically, they want you to do this. They want you to remove the relay, install a jumper terminal on the load side contacts, and then check your motor for power. That's basically what you're doing. So jump the relay, and then what we're doing is if the relay, I'm sorry, I'm skipping a step. Test the relay, replace under diagnosis. If relay is stuck on, pump motor may be damaged. If relay is okay, bleed the high pressure fluid. And then what we're doing is removing the relay, and I jumped a gun on you here. That's when we do this jumper. There's an important step right here, guys, and that is that we need to bleed the high pressure fluid from the modulator bleed screw before we do this test. And so I pulled that up too, and it's really simple. There's just a bleed screw on top of this ABS unit, and we're just taking that, loosening it into a container before you run the pump. The reason they're having you do that is we don't want to over pressurize this modulator from this pump. So we bleed the pressure out, then we energize the pump and do our check. So we have to do that, and we will do that. Take you to the diagram now. And we'll look at the relay on here, and I'll show you how I want to test it. I don't like jumping the load sides of relays because it's too easy to jump the control side, and you can fry computers if you jump the control side. Looking at this pump relay right here, there's your pump. You can see that it's grounded all the time. That means it's power side switched by this relay. You see when that fuse or when this switch closes, it's going to get power from this fuse down to the motor. Now what closes this switch would be this coil. So we look at a relay, very typical. We need this coil to energize, to close the switch. A coil needs a power and a ground. We follow this pink wire, it comes up to this fuse, so we know for a fact that this side is power. We follow this blue wire. On this circuit, what we find is the blue wire goes to the engine computer. So what we know right away about this ground, sorry, just gave that away. What we know right away about this control wire is this is a ground side switch circuit. There's going to be a transistor inside the computer right here that's going to ground this circuit. It's a switched ground. Okay? So what we want to do in our test, rather than following what the manufacturer flowchart tells us to do, which is remove the relay and then jump the load side and focus on the pump, I want to focus on the whole control circuit and the pump at the same time. So what we need to do is we need to provide the ground for this relay that the computer does, and we're going to use a test light to do it. You can do it up here, test light to ground. The reason I like to use a test light is a buffer in case you use the wrong polarity. Now, we don't want to use the wrong polarity, but in case you did, all that would happen is the light would light if you accidentally jumped that to battery positive. If you were using a jumper wire and went to battery positive right here, and this driver happened to be on, it is that fast. You just cooked the computer. So I like the test light for this. Test light that I use with the incandescent bulb has enough current that it will be able to carry the relay coil current enough to energize this, make a magnetic field, and pull the relay shut. And when we do that, we should hear the relay click, and we should get 12 volts at this pump motor. Now remember, we were at the computer checking powers and grounds when we started this, so we chose to do it down here. We took our test light here at the computer pin to ground, and I like it better here, truthfully, because it also checks this entire control wire. So we're going to do that step next. We're going to take that test light and we're going to jump that circuit to ground, give the ground that the computer would normally give, make the relay energize, and look for power up here at our pump motor. We want to see power right there. And then of course we can check our ground too. Once we load that pump, we can check our power and ground to that pump motor. So I'm going to take you to the car now. We're going to do this step, test light to ground on the control wire at the computer while we're monitoring our voltage at our pump connector. Alright, so we're at the ABS module, which is behind the passenger seat right here, pretty much right below the rear glass is where this ABS unit is. And I have my control wire T-pinned already. I know that this gets a ground, so I have my test light connected to ground, incandescent test light. And now before we do this, let's talk about the safety again. You have to make sure that your pump motor circuit, or that modulator circuit, that we bleed the pressure out of it. Now we've done that already, and when we cracked that bleeder loose, there was no pressure in the system at all. So pretty sure this pump hasn't been running for a while. And when you do this step, according to Mitchell, you don't want to do this for any period of time because you can build too much pressure and you can damage that modulator. So this is a momentary test, and what you really want is a partner doing this. Jump the circuit, check your motor controls. Don't do it for any long period of time. Here's the test. I'm not sure if the camera's going to pick up that relay clicking. And you see my test light just barely lighting. It's dim. And the reason for that is we're not dropping all of the voltage across the coil of that relay. Most of it though, it's enough to energize it. I heard the relay click. So I'm going to go up front, show you these voltage readings while I'm energizing this back here. So next step was to monitor the voltage on this pump motor circuit. This is the pump motor right here. There's a 2-pin connector that runs this way, has the power and ground in it. I have the harness side of this back probed on the power wire. So I'm going to show you this voltage on this wire with the relay energized and de-energized. Using the Vantage Pro here for this one. And this is what I saw on this circuit before energizing the relay. I see 10.8 volts on this circuit. Now I'm going to let you watch this while I energize the relay. I just turned it on and off 3 times. You see our voltage did go up. Get you a better shot of that. We actually went up to battery voltage of 12.6. The tops of these little square waves here is when I turned that relay on. So we are getting power here. And what we didn't like was that we had 10.8 volts when we didn't have power. So what I wanted to see with that is what kind of voltage signal is this? And by that I'm saying, is it a strong one? Is it a weak one? This is going to answer a lot of questions for me. So it's pretty simple. To address that, I'm going to use a test light. And what I'm going to do too is change the scale so you can see everything now. We don't really need the graph mode here. I'm going to go right to my voltmeter, which will be a little bit easier for everybody to see everything I'm doing at the same time. And let me back us up. Okay, so I want to see what kind of signal this is. I'm going to take a simple test light. Important that it's incandescent. Use an LED test light, things are going to change on this test. I'm going to go to ground with this test light, just right to the battery. Really any ground, doesn't matter. Really, and what I'm looking for is this 10 volts going to light my test light? You know what we're thinking right now, with the relay off, why are we reading voltage here? You know, maybe we have a cross between another circuit and it's a short to power, and that's why we have a motor circuit fault. Well, take a look at the meter when I put this test light on here. You're going to notice two things. One, the voltage drops to 0. I get a good connection here. And two, my test light's not lighting. So what kind of signal is that? Well, I'm going to call that a weak signal. 10.8 volts. Why am I reading 10.8 volts on this circuit with the circuit off, and when I think I should be reading 0? So that's in question here. Let's go back to the wiring diagram. Okay, let's see if you guys can follow this. Computer controls the pump relay on this blue line right here. We give this a ground. That's going to energize the relay, makes a coil, magnetic field, pulls the switch closed, runs the pump. Something that we didn't look at the first time I showed you the diagram was this little tie-in right here. And as you can see, that is on the load side of the pump motor circuit. So when this switch closes, not only is it powering up the pump, but it's also sending 12 volts in this direction up through a fuse and then down to the engine computer on pin 17. It's a brown yellow wire. It just says MCK. Probably stands for motor circuit is my guess. Guys, listen. This is an input. This is an input. Now what would that input be for? That is for trouble code diagnosis of this motor circuit. Now think about the logic here. The computer is the one that's controlling the relay, right? So of course the computer knows when the circuit's on and off. When the computer commands this transistor to turn on, it wants to see what voltage right here. The relay should energize, we should make a field, the switch should close, the motor should run, the computer wants to see 12 volts at this location. 12 volts equals motor is on and running. Okay? What we would think with the circuit off is 0 volts would be off. And that's what we should see. But we are seeing 10.8 volts with the circuit off. So the reason I'm shooting this video, this is the primary reason, is there's a bias voltage on this circuit that's used for diagnostics. I've talked about this in other circuitry. I've talked about it with potentiometers, where we use a bias line and that resistor in between the reference and the signal line. I've talked about this with O2 sensors. I've talked about this with ABS wheel speed sensors, and I'm talking about it here with this motor circuit. In fact, I also have shared this with you on a GM fuel pump circuit where the relay had a bias voltage. This has a bias line. So I want to walk you through what we're looking at and why we're seeing 10.8 volts on this circuit, and how easy this circuit is to troubleshoot once you know what this is there for. Okay, just to review again where we were with the car, the circuit is off right now. I am on the feed wire to the pump motor, reading 10.69 volts. The battery voltage is probably a little bit lower from my last clip. Go ahead and energize the relay for me again. Let's watch the voltage. So circuit energized, we have 12 volts. Circuit de-energized, let it go. We have 1069. Now remember, damage can occur to this unit if you run this pump motor too long. This pump is not running. I want to be clear about that. If you were doing tests on a running motor, you are instructed to bleed this between runs so you don't damage this unit. Our motor is not running, so we're okay in doing what we're doing. So we're pretty confident that what we're looking at here is a bias. And at this point, what I did is I actually smacked on the motor. And the thought process here is this bias line actually gets pulled to ground through the brush motor contacts. And what we can say is our brush motor contacts are faulty, or we have a bad ground. So the ground test would have been to come over and back probe the ground, look at our voltage with the circuit energized. It was low, that wasn't our problem. Unfortunately, I can't simulate that. What I have right now, and I didn't tell you before, is I have this connector unplugged a little bit to simulate what we saw. At this point, again, what we did, smacked on the motor, this dropped down to 0 volts. We were correct in our assumption. It was a bias voltage, and our motor circuit is faulty internal. So watch, I'm gonna plug it in, and you see with good contact with the brushes, that pulls that line down to 0. Go ahead and energize that for me. Okay, good, let off. So you heard the pump motor run that time, and right now we start the car, the check engine light, sorry, not check engine light, the ABS light is off, and our fault is gone. And what we had hoped for this guy is that just the fact that leaving this power cable off for maybe a long period of time, we developed resistance in the contacts of the brush and the motor, and we hoped that getting it up and running would be enough to get him by for a while, and it lasted maybe a day before the light came back on and we developed pump motor codes again. So we are having contact issues with the brushes on this motor. There is a bias line voltage used for diagnostic purposes. I'm going to come back to the wiring diagram one more time to explain that to you a little bit further. All right, so final overview of this Honda ABS system. I did a redrawing of the diagram to make it a little bit easier to understand what we were looking at. So without looking at this area in here yet, we didn't have that. What it said was motor circuit, I think. It was MCK is all it said on the wiring diagram. We didn't know what that was. Looking at the relay, we knew that this was the feed side of the relay here. It goes to a fuse right here. We knew that this side was our controlled ground, and we knew that simply by the fact that there was a fuse right there. So the computer controls the ground side of this ABS pump motor relay. As soon as this completes the circuit to ground, this is going to make a magnetic field. It's going to pull this switch closed. We're going to send power down to our motor. We have 12 volts at that point. At the same time it's being sent to the motor, it's also being sent this direction through another fuse on its way to the computer, and that's where our bias line comes into play. What we were seeing at this location, we were seeing 10.8 volts with the circuit off. And when we first saw this, we weren't 100% sure where it was coming from yet. So I took a test light right here to ground, and what I saw was this 10.8 volts drop to 0 volts. It was a really weak 10.8 volts. Didn't light my test light. 10.8 would be enough to light a test light. it didn't light my test light, pulled the voltage all the way down to ground. So that made me go back to the diagram, look at the circuit, as I showed in that last clip. I think I talked about it. We looked at this line and said to ourselves, there's something going on here on this MCK circuit, and what we realized is this is, as I said, this is an input that when the computer controls this transistor, it watches this line for an input for motor trouble codes. How is this thing generating a motor circuit trouble code when the motor never ran? It's not using some kind of pressure sensor. It's using a voltage level to check the circuit. So what it wants to see in the logic in here, what it wants to see would be transistor on. With the transistor circuit on, our relay up here would be energized. Computer wants to see 12. So I said this in the last segment. 12 would be circuit on, and with the circuit off, we want to see 0 volts with the circuit off. But what we were seeing circuit off is 10.8 volts. Where's it coming from? It's coming from this right here. Let me clear this. With this circuit off, can you guys see that this doesn't attach to anything except for the computer and the motor? And inside of a DC electric motor, what we have is a commutator segment, you have a positive brush, you have a negative brush. And what you have is a bunch of wiring in that motor. When you have a good DC brush type electric motor, if you were to run an ohm meter across a good DC electric motor, you will read 0 ohms of resistance with that motor stationary. DC electric motors produce resistance as they spin, counter electromotive force. I don't want to go through that right now, but the point is that a good DC electric motor will have 0 ohms of resistance. So if this line's going to ground and this line is going to our computer, which is right here, if you look at it, that's what we got. This side's going to ground, negative brush is going to ground, positive brush is going to the computer. The computer's actually supplying a voltage across the resistor, and I'm going to assume this is 12 volts. I know we have 10.8, but call that a 12 volt circuit. As long as the motor contacts and the brushes are good, what we have is basically a wire that's going straight to ground. And so even though we're sending voltage in this direction, again, we're going across the resistor here, that circuit, it's going to drop straight to ground because of this resistor right here. Very high ohm resistor. We could probably assume 100,000 ohm resistor. With a good motor, with the circuit off, we should have 0 volts in this location. Little voltage sensing circuit. Again, I'm not the engineer. I don't know what that looks like inside, but I'm telling you this is how it works. The computer watches this line right here. And it knew by a bias voltage, we could call this a bias, that the motor brushes or the motor circuit had a problem, because what it saw, what it should see with the circuit off is 0, but what it was seeing off was 10.8, and where was the trouble code coming from? It was coming from that. So again, with the circuit commanded off, okay? With the circuit commanded off, what does the computer want to see right here? At that point, it wants to see 0 volts. And if it sees 0 volts, what that means is there is continuity on this line. More importantly, there is continuity through the motor circuit. If it sees 0 volts. When will it see higher than 0 would be in a normal situation if the circuit if our circuit is commanded on, computer wants to see 12 volts right here in this location. That would be normal. And the reason that would happen is this switch would close. We'd send 12 volts through the motor and also 12 volts this way, and it would feed through to the computer and read 12 volts at this location. It doesn't matter that there's still a trace voltage here. That has nothing to do with it. It reads 12 when the circuit is energized. That's what it should be doing. The only other time we would read high voltage in this location with the circuit off would be when we have an open here. This resistor would have no ground. Where's this resistor getting its ground from? It's getting its ground through the electric motor. No ground on this resistor, your voltage will be high here. And in our case, we read 10.8. And I said that it probably is 12 because what we're doing is we're connecting a meter up to this. Remember that? And our meter's going to ground, and our meter is probably about 2 mega ohms, maybe 10 mega ohms, and we're actually drawing some of that voltage to ground through a 2 mega ohm scope. Now you might be thinking, well, that's a lot of resistance. How's that going to drop voltage? What that does is shows you how weak of a bias line that this is. We saw that earlier too when we connected multiple scopes to the same circuit, how it was pulling a bias voltage down. So if you would have put, say, 2 or 3, in a class situation where we may have 4 scopes connected to the same line, that voltage is going to be even lower still. And that really explains too why the test light, we put the test light on that circuit, it wouldn't light the test light and pulled it all the way to ground. What else would give me that 10.8 volts would be if that fuse was blown right there. Because that bias line then would be not able to make it through to the motor to get to ground. So why is that fuse there? The only answer I can give you for that fuse, guys, this is a hot feed, right? It comes from the motor. What if this wire shorted to ground in here without this fuse? Is it would blow the pump motor fuse. So the only thing I can figure is this is there to protect this wire only. And again, I'm not the engineer. I don't know why they did it. They really don't need it. If you think about it, if this wire shorted to ground, it would blow that fuse. But in any case, they do put a fuse on that. So open wire anywhere in here, blown fuse, or one more thing would be this motor connection. There is no connection, that we have a brush contact problem. And so come down here, that one of these brushes is not making contact, and so there's no continuity through this. And that's what we had. And I wish I could have shown it, but when we realized that this was a bias, I smacked on the motor, and we know electric motors, fuel pumps, we do this all the time. The fuel pump doesn't run, you smack the tank and the pump runs. That's exactly what we did here. And it was cool because we were looking at this in a graphing meter mode, and we read a flat line 10.8, and as soon as I started smacking on the motor, this line started to drop and went all the way down to 0 volts with a couple more smacks. And then we redid our test light thing where we energized the relay, and the relay closed, and then the pump ran, and this 0 line went up to 12, and we heard the pump motor run. And so that whole thing was a bias voltage that we were looking at. But I think it's pretty cool to know about, because how much does that help you in your diagnosis to know that it's there, number one, and then number two is how much could that mess you up? And it did for us when we first started. Our huge question here is, why are we reading almost battery voltage on this circuit when the circuit's off and it shouldn't be there? Someone unfortunately may put a computer in this for something like that. It is completely normal, and we are seeing this type of thing all over the car, from oxygen sensors to ABS wheel speed sensors to relay coils, Power and ground side switch circuits. I have an example of that in section 3 in my book, where we do a air suspension solenoid that had a bias line. Same thing. This is all over the car. So again, the emphasis with this video is this bias voltage, what it is, how to use it, how to recognize it, look for it. It'll help you. Okay, final review for this. For this pump to run, right here, we need this switch to close. For this switch to close, this coil needs to make a magnetic field. We have power here, it's hot all the time. Computer provides a ground through the transistor, so computer grounds it, energizes the circuit, gives this coil a ground. This thing makes a magnetic field, pulls the switch closed. Switch closes, we send power to the motor runs. At the same time, the computer watches that motor circuit, and it says that it is good if it reads 12 volts while this is being commanded on. If this is being commanded on and it reads 0 volts up here, we're going to get a trouble code. If this is being commanded off and we have high voltage here above 0, we're going to get a trouble code. And that comes from this bias line. Poor brush contact is what we had, so we send voltage across a resistor that normally, under a normal situation, would be finding a ground through the pump motor. And with that ground there, we have a full voltage drop on that resistor. High voltage on this side, we'll call it 12. And 0 on this side, as long as the motor is intact and it has a ground through the brushes. Our brushes were bad, and so we read 10.8 at the computer in this location, and we get an immediate DTC code 1-2 pump motor circuit fault. How easy is this to troubleshoot if you know the diagram? You don't have to follow that stupid flow chart, right? And we look at this, from now on, I see a Honda and I know this pump motor circuit's designed this way. And I look at this motor with the circuit off, key on, and I have a pump motor code. And I come over here and look at I have 10.8 volts on that motor. I'm done already. This thing needs a pump motor. How's my wiring? How's my computer? It's all good. I may come over here and check the ground and make sure my ground's good, because if we have a bad ground here, we might read 10.8 on the ground, which would tell me my ground is open. So do that check. But other than that, you're done. Smack on the motor. Watch that voltage drop. How fast was that diagnosis? You took an hour flow chart, 2-hour flow chart, and you cut it down to 30 seconds. So learn the diagrams, learn the systems, forget about that flow chart. Use the flow chart as a guide. I mean, we used that flow chart for a safety measure, didn't we? We learned that if we run this pump motor for too long, we're going to damage something. So please, I'm not saying never use a flow chart, but we want to develop our own testing methods. And we're not tied down to somebody else's testing method. We can use our own. Understand the system, you'll be able to troubleshoot that car so much easier.